Okay, so we are just preparing two adhesive bonded joints to demonstrate something for the next session. Never mix the caps, of course. Now, so one of them will be a peel strength test joint, and one will be a pure shear test joint. If you have fast epoxy like this, say 5-minute epoxy, and for some reason you need longer working time, just mix it on a chilled piece of metal, piece of aluminum, because if it's cold, the working time is much longer. Okay, so now just prepare one area, and it's a good thing actually put some epoxy on both sides. Like this. Put it together, put a weight on it, and make it set. Do the same here. Now, because of the small taper of the water jet, you can always assemble it from the direction the hole is slightly bigger. Again, you put epoxy on both surfaces. Now it says 5-minute epoxy, but it really, to get any reasonable strength, you have to wait an hour or... Okay, good. So, put this to set, and we are done. Okay, so this is an introduction of how to build large structures using the water jet. And this is in particular structures which are temporary. You want to do some experiment, you want to have some temporary setup. Because if you want to build large structures in a permanent way, the cheapest and the simplest is still welding. Just take some pipe, some plates, and you weld it all up. But welding has two problems for the student, say, or researcher. The first problem is it's hard to learn to become a good welder because it's something which takes a lot of experience and skill. And the second problem welding has, even for a good welder, that welding causes very large distortions in everything you weld. So if I had to connect two pieces by weld, and I say I welded the corner, as the weld cools, it will pull the parts. And you have to do many, many tricks to minimize that distortion, and even then the part is distorted. So then you have to machine the areas to correct the distortion, so it's a lot of work to build structures by welding, but that's the only way to do it if you need strength. But if you don't need the strength, you just need the stiffness, and we just saw a demo that most of the times that's what you want to see. A very good way to build large structures is by adhesive bonding. Now, let's say we need to build a structure which is 1 meter by 2 meters to hold some instruments or some experiences. So what I did is I just did a 1/10 scale model, because I'm just in order not to waste 1 meter aluminum plates, which is expensive. So let's imagine this is 1/10 of full size, and I needed some structure to hold some very precise beam. Let's say I have a granite beam here, and I want to hold it very, very accurately in space. So a good way to build these structures is by making some end plates from aluminum plate and braces from pipes. Now, it's not the only way. You can make the braces also from aluminum plate, and you can make many variations. But the idea is that you cut all the parts on the water jet and you assemble it by adhesive bonding. So you can here take advantage again of the fact that the water jet cuts with a very small taper. So you can make the parts, they fit in easily from one side, but they don't fit so easily from the other side because of the taper. The taper here is only like 50 micron. But what it means that you can temporarily assemble the structure just by pressing it in, and you can test everything before you bond it together, and that's very, very convenient. So say you can assemble the structure, and imagine this is 1/10 of the real size, and test everything and modify, and then when it's all ready, you knock it down, and then you bond it, and then it's permanent. But But even when it's permanent, the nice thing about it that months later, when the experiment is finished, you can heat up the whole structure, either with a torch or in an oven, and knock it apart. Because the same thing I did here without the epoxy, if this was heated up to about 150 degrees Celsius, okay, or say roughly 300 degrees F, I could actually knock it apart, even if it was bonded with epoxy. Now, the one thing when you look at that, you say, why not buy these extrusions which come with T-slots and they are designed for rapid assembly and disassembly, and they come in all sizes, typically 2 by 2 inch cross-section or 3 by 3 inch cross-section. And the answer is all these structures are not rigid. Because if you take a structure like this and bolt it together at the corners and so on, the rigidity is way below a structure which is adhesively bonded like this, because at the end, if you look at the system with the T-slots and a screw, at the end, if you bend it, it stretches the screw. Okay, so it has a huge lever and it stretches the screw, and sideways, there is nothing stopping it from twisting. So as long as there is a little bit of twist possible or a little bit of play possible, there is no rigidity in the structure. So it is okay for things which don't need any accuracy, like an enclosure, a cover, or something to hold a table. But if this also has to provide the accuracy, not just an enclosure, it has to be all rigidly connected everywhere. And it has to be over-constrained heavily and basically made into one piece. So to make it into one piece, as I said, if you don't want to weld it, which you could do the same thing and weld it, okay? But if you don't want to weld it, one of the best ways is adhesive joints. Now, while you do that, you think of all the things you would need. For example, you'll need some bracket here to hold something else. So you cut out some holes, very much like woodwork, and you make a bracket like this, and the bracket would fit into the holes. Again, you take advantage of the slight taper. Okay, so you see it doesn't fit in one way, but it fits in the other way. And what you do actually here is I just ground on the sander. I just sanded this down a little bit to give it a minute slope. And because it has a minute slope, it's actually locking like a wedge. So if I put it in, even without adhesive, it will lock into one piece. So if I do that, it locks together like a wedge, and you'll be surprised how strong this bond is without any adhesive. So if I want to take it out, so if I want to remove that piece, I would have to hammer pretty hard to get it out. Okay. Now, of course, at the end you will put adhesive on it. Now, so say if I have these plates and I need, so any kind of brackets that I need, I would either add to the plates, or if I need some support in the middle, let's say if this is the assembly and I needed some assembly in the middle, I would make other plates which slide on the pipes and hold things in the middle. So you'd think out the whole thing in 3D, think of any support point, any bracket you need, and assemble it all at once. Now, if you need a reference surface, you assemble the whole thing on top of a granite plate. For example, if it's very important that this surface and this surface and this surface are coplanar, I wouldn't assemble it like this. I would assemble it upside down on a granite plate and let it cure on the granite plate. And this way, when I pick it up, everything is automatically planar. Now, the other thing you do, all the parts which are not permanent, you can lock in with some flexure clamps. So, for example, if I look at this assembly, and let's just assemble it now. Okay, let's see which side is which. Yeah, that's the correct side. So let's just assemble. I wouldn't use adhesive now, but you can imagine the ends are sandblasted. The inside of the cut of the water jet behaves like sandblasted. So all I have to do is just smear adhesive on both sides and assemble it, which I wouldn't just do it now. And I put it together like this. Okay. Okay. Yeah. Assemble. It's amazingly rigid, even without any adhesive. Now, and of course, I would assemble all these brackets that I need. The main benefit here is the self-registration, or what's called self-jigging. I don't need any jigs to assemble it accurately because everything locks in slots. It's all automatically jigged. Now, of course, this has to be made planar because it can still twist. So if I would assemble it on a granite plate, I would just force it to be planar. Now it's planar. You can check it on the granite plate. Yeah. Okay. Now, if I want to hold removable parts, let's say I want to hold this granite beam, I would use, remember it's all 1/10 of actual size, so it's actually a huge structure. I would use flexure clamps, and the way you make a flexure clamp, you cut a slot and you put in something which can expand and use this as a clamp. So the easiest way to expand is you tap it with a taper thread, a taper pipe thread. As you know, all pipe threads are tapered, so you use a regular plug, which is used on plumbing, and they come in all sizes, from an 1/8 of an 1/16 of an inch pipe size to huge plugs. Okay, you tap the hole with a pipe thread. Okay, and then this one is already tapped. When you put in the plug, it will expand and clamp. And that works very, very well. For example, if I slide in a granite beam, this hole is quite accurate. Okay, so here I have a granite beam, which is a very nice fit. It perfectly fits in, but I can slide it. Okay, the moment I turn in this plug, okay, it's locked in, can't move it. And I can disassemble it, and it's a very, very good clamping system because it doesn't put local load, it spreads the load. Say the inexperienced person would put a set screw in, and that's a very bad idea because the set screw would crack the granite because it puts all the load at one point. Okay, and in any case it's not accurate, even if it wasn't brittle. It's not accurate because the set screw deforms it. It puts all the pressure on one point. While if you put this flexure clamp, it just expands in a gradual, very gentle arc and spreads the pressure on the whole granite. So any kind of flexure clamps are much, much superior to set screws. Even if you have a pulley and you want to clamp a pulley, or you want to clamp anything, you water jet cut a flexure clamp into it rather than a set screw. Okay. Now the next thing we want to, and let's take it apart. You get a huge leverage here, of course, because that thread angle is less than 2 degrees. So you get the leverage of the thread. You get one lever plus the leverage of the wedge. So you can generate many, many tons of force just by one turn. Okay. And once you loosen it, it's completely loose. Okay. So I want to explain something about adhesive joints. A proper adhesive joint should always be designed to work in shear mode, like this. Next best thing is designed in tension, which is much weaker, and never be designed to work in peel mode. And to demonstrate this, let's look at the samples we prepared earlier. These are the two samples we prepared earlier with 5-minute epoxy. One is for peel mode and one is for pure shear mode. So this was sandblasted, properly done, properly cured by all the rules. And if I do it in peel mode, it has 0 strength, which is surprising. The epoxy was spread and everything was good, it has 0 strength. And if you try it with any other adhesive, you get the same results. So never design something. Sometimes you don't think you're designing in peel mode, but it's actually in peel mode. For example, if you make a bracket, let's say, if you glue a bracket like this, you don't think the joint is loaded in peel mode because you think it's tension, but it's not, because if you bend it, if you try to bend this bracket, it will peel off from one end. So many joints that you don't think will be failing in peel mode are actually will fail in peel mode. That, even things like this, okay, you say, well, that's in shear mode, but not, because it lifts up and it's in peel mode, okay? So basically any design like this will fail instantly, okay? So if you compare this area of adhesive, it's actually more area of adhesive than I have here. And let's go and do a test and see the strength of this. And you'll see this is much stronger in 1 second, but I want you to think of the explanation. Why is the peel mode so hopeless and the shear mode so good? And the answer is that the shear mode puts the load at once on the whole joint, because everything wants to move, so the load is instantly applied to the whole area. Peel mode puts all the load on one line, because just the line where it starts lifting off, anything behind it doesn't see the load. So since all the load is concentrated on one line, which means geometrically zero area, it has to fail. Okay, and that's why you should be very, very careful. The same thing is true for soldering. If this was soldered, not done with epoxy, I could still rip it apart by hand. Okay, so let's just test the strength of this for comparison. Okay, so now we're going to test the properly designed joint, which is a shear joint. This measures the pressure in tons from 0 to 30 tons. Okay, it didn't take very long actually, it only took like 2 tons, but still 2 tons compared to 0 is not bad. Okay. Yeah, it broke the joint at 2 tons. This is strictly proportional to area. So if this is 1/10 scale, if this was full size, would have been 20 tons, because actually would have been 10 times, 100 times bigger, because the area would be 100 times bigger. So if this was 10 times scale, the area would be 100 times bigger, would be 200 tons, okay, which is very respectable. Okay, so just a quick note about adhesives. There are only about 4 types of different adhesives you need in a lab, and the most commonly used is epoxy, like 5-minute epoxy, because as its name says, you don't have to wait too long. Now, second adhesive, which is very, very useful, is silicone RTV. And the uniqueness of RTV is, first, it's the only adhesive which can take a high temperature among common adhesives. The clear RTV, the regular one, can easily take 250 degrees C. The red one, you can buy the same thing with a different cure system, which is red. It's iron cure. It can take about 300 degrees C or maybe a bit more. So it's very good to anything which gets hot, heaters and so on. RTV has another very interesting property, or two. First, it stays elastic forever. And B, it makes a tenacious bond to glass and certain ceramics without even sandblasting or anything, because all other adhesives, as I explained under paintings, cannot really be used well if the surface is not prepared, at least by bluing, but preferably by sandblasting. So it's the same as paint preparation. Either you rub it with bathroom cleaner like Comet or Ajax, or you blue it, or you sandblast, but preferably you sandblast. RTV is the only adhesive which doesn't need that for certain materials, because it forms a tenacious chemical bond, especially to glass. You can see in aquariums where they edge glue aquariums now from glass plates with RTV. That's good. Now, so we have epoxy, RTV. A very, very useful adhesive is polyurethane. Polyurethane adhesive has some unique properties. The first property, it is a bit flexible and bonds tenaciously to things like rubber and flexible materials. None of the other adhesives bond well to slightly flexible materials because the adhesives are rigid and somehow they don't hold. Polyurethanes, certain types, are also designed to foam up by themselves and fill all the gaps. Like this is just says on it Gorilla Glue, but it's basically a high quality polyurethane adhesive. It is excellent for bonding sheets together. It has good peel strength. It's actually a much better adhesive than epoxy, but has to cure overnight. And the last adhesive which is useful is just some spray contact cement. If you want to cover something with a large sheet with a uniformly thin adhesive, you just spray. Of course, contact cement you have to spray both sides. The other adhesives is enough to apply to one side. So if I do that peel test I've done before by gluing together two strips and trying to peel them apart, you've seen before that the epoxy had zero strength basically. One reason epoxy will have zero strength in peel, because when you peel, all the stress is concentrated in one line where it wants to separate. So theoretically, the stress, if the adhesive is rigid, the stress is nearly infinite because it's all one line, it'll break. If you did the same test with a semi-flexible adhesive like polyurethane, or especially with RTV, the peel strength will be better because it will stretch. The adhesive will stretch and the material behind the line will also stretch, so the stress will be distributed over a bigger area. So anything which has to flex and bend and may end up in peel mode, you cannot use epoxy, but you can use RTV or polyurethane. But preferably don't design joints to operate in this mode, but when you have, you can't use epoxy at all. So this is basically all what you need to know about adhesives, unless you get into really exotic stuff. There's also another family of acrylic adhesives, which is a little bit in between these two in properties, but you usually really, in a normal lab environment, what you see here is all the adhesives you need. Now, another adhesive which is commonly used, and I don't have here, is cyanoacrylates, which what's known as super glues, or magic glue, or super glue. Now, they are not very good adhesives for two reasons. A, they are very rigid, so the joint can fall off from a shock, can break under a shock load very quickly. They are very good for rubber because they bond instantly, so they're good for O-rings. But they have another problem which is very devious, that they emit some gas slowly. So if you glue anything with super glue and there is any optics in the same box, the optics will fog up within a few weeks and be ruined. And also they have some bad effect on some plastics. They cause the plastics to craze. Craze meaning develop micro cracks. So there is some side effects of super glue that you don't see when you glue it, but when you come back a month later, you find out all kinds of plastic pieces are cracked and any optical part is covered by a white film. So it's basically better to be avoided for scientific work, because other adhesives don't outgas much, and you can bake them. You can bake them and stop the outgassing to a great degree, because anything which is in a sealed box, you're always worried about outgassing from adhesives. That's why when you build lasers or other things, you are not allowed to use any of those because of the ongoing outgassing. But at least you can accelerate the outgassing by baking. But superglues have a lot of bad outgassing and kind of strange materials come out of them. So unless you really need them, they are not recommended adhesives for normal scientific work. Okay, one other thing you have to be careful about, because of the high expansion coefficients of plastics and of all adhesives, which are basically polymers, is when you need things to stay precise with temperature. So I already mentioned that the temperature expansion of all the polymers are an order of magnitude roughly more than metals, unless they are heavily filled. So when you would bond a mirror, say with epoxy or RTV, to a piece of metal, so you have to worry about two things. First, the glass and the metal have different expansion coefficients, so you have to make sure over the size of the mirror it wouldn't be a problem. But you have to think of something else too. That bonding layer will expand with temperature 10 times faster than the metal. So if this mirror is just acting as a head-on mirror or 45-degree mirror, the problem is not very big, because if this mirror will shift parallel, usually it's not a problem. Let's say you have a 50 micron bond layer, Even if it changes 10% in thickness, it's only 5 microns. A 5 micron parallel shift is usually not a problem for a lens or a mirror. But if you bond it and you fill the adhesive as a wedge, let's say you want to align it, and you align it and then you put epoxy behind it, which forms a wedge. Then the angle of the mirror will change with temperature, and you have a big multiplier effect because of the optical lever. And it's true not just for a mirror, it's true for any structure you bond. If you bond a right angle bracket, as long as it's parallel, it will move up and down a bit, a few microns. But if it's a bracket which is bonded with a wedge, it will tilt, and the error will be multiplied by the length. So that's something to keep in mind.